So like I said, I wanted to trace this idea of quantized, that the world is quantized. What does that mean by quantized? Well, think of a ramp. When you're walking along a ramp, you can stop at any point on that ramp and you can calculate your potential energy. So your potential energy on that ramp is infinitely variable. You could go one atom higher and have sort of 1 atoms of elevation more potential energy, just calculating your mass and gravity, right? But quantum mechanics says that it's more like stairs. So like in the hallway here in the stairwell, you are on the first step or the second step, but you can't really be between, and not be moving. I mean, you can try for a while, but your thighs are going to get tired, right? Hold yourself in between the 2 stairs. So you're going to transition from step 1 to step 2 to step 3. And that's what we mean by quantized thinking. Quantum just means a unit. So that word quantum just means a unit, like a unit of energy. And so let's trace the history of this idea, because that's really strange. Why can't an atom or an electron have any energy that it wants? This seems to be a limitation in nature. And where would these limitations come from? And how would they get actually put onto electrons and nuclei? And so let's go way back, before Einstein, before Schrodinger, before Planck and Boltzmann. Some of these names you may have heard of, some you maybe haven't. Before Newton, you get back to 1629, Rene Descartes. So you've heard of Cartesian coordinates? This guy. Okay, so this is where just even our coordinate system comes from. He wrote this book called Rules for the Direction of the Mind, and he was trying to think, how can we understand and find the truth? And so in rule number 4, he said there's a need of a method for finding out the truth, because truth is elusive, right? You just read the newspaper, and get multiple papers, and you see all kinds of different opinions on the events of the day. And so how do we find the truth? Well, in terms of Descartes, he said that mathematics was a good way to find the truth. And he said there is, in the human mind, this something that we may call divine, where they're scattered the first germs of useful modes of thought. And so this when I read this, I thought, this is really cool, because it's almost like it's contagious, these ideas that we have. You might hear about memes, and memes are also kind of like genes. They mutate, they grow, they spread, okay? And so this is kind of what we're seeing now in our current culture, how fast a meme grows and spreads and goes from person to person and introduces these little germs of thought in different people's ideas. Well, Descartes kind of picked up on this. And this first germ of useful thought for him was mathematics. And so he wrote a book, Geometry, and sort of mapping things out. That's where our Cartesian coordinate system comes from, and angles and triangles and circles and squares and so on. He started working with geometry very early, and this inspired a young Isaac Newton to begin mathematical study. Now, you guys have heard of Newton, right? In fact, he invented calculus, but he wouldn't have invented calculus if he hadn't started with geometry that was written by Descartes. And so this idea of math being useful to describe nature got caught by Newton. Everybody talks about the apple falling on his head and him discovering gravity and all of those things. But it was really from that germ of a useful thought that math might be helpful in this situation that caused him to come up with the gravitational laws and so on of his day. In fact, his math was so good at describing nature that he just took it as far as you might be able to go. And so it was so successful that we really had an idea that we could predict the future. Now think about this. If you have a Newtonian physics, and you guys have taken physics, the cannonball problem, right? You got a cannonball, the ball leaves the cannon, and so it's in so many feet per second, at such and such angle, where will it land? Do you realize you're predicting the future? You're predicting the future. That's crazy, isn't it? You're shooting a ball into space and it's landing someplace, and you've predicted where it's going to land. We do the same thing with our satellites. We do the same thing with space shuttle, SpaceX. All of those things are based upon Newtonian physics. an orbit of a satellite is just so big that it's spinning, and it's going up, and then it'll reach apogee, and then it'll start coming down, and it'll spiral back down into the Earth's atmosphere if we don't boost it a little bit. So it's no different than a parabola. It's just a parabola that goes around the Earth thousands of times. It's growing, and then it's really flat at the top, and then it starts to spiral back down, and it will hit the Earth. And we can predict exactly when it's going to come back down and when it's going to hit the Earth, okay, using Newtonian physics. So this was an amazing thing. I mean, we applied Newtonian physics to every aspect of life, and it created a lot of fantastic advancements. I mean, you get from that all of thermodynamics and all of engineering, the Industrial Revolution, all of that using Newtonian physics. Incredibly successful. In fact, this is an English poet at the time, and he wrote, "Nature and nature's laws lay hid in night. And God said, let Newton be, and all was light." So, you're sort of playing off of Genesis, where God said, let there be light. Well, this Alexander Pope in his Poetic said, Newton's so important, all God had to do was say, let Newton be, and then everything was illuminated. Okay. That's bragging, I tell you. And so these germs of useful modes of thought went from Descartes to Newton through math, and then more math into Ludwig Boltzmann. And he started studying gas velocities and equilibrium and pressures. Think about the whole Industrial Revolution. We had steam power. So gas pressure was an incredibly important aspect of life. And as Boltzmann was sort of studying the velocities of gases, he was what we would call an atomist. He believed that the atoms and molecules existed, whereas others thought it was just like a field, like there were not individual particles of gas. And they actually had such a huge battle, the positivists, as they were called, these philosophers that said atoms didn't exist because you couldn't see them. If you can't observe them, then they can't exist. Drove Boltzmann into depression, and he committed suicide over all of this. So, pretty tragic story. But what he did was he used quantized gas velocities just to simplify the math. So in his paper, he said, I'm not saying that gases can only have certain velocities, but it simplifies the math. And so if we start with discrete velocities, and that's the word discrete, you want to write that down. Discrete, you can put roughly equals quantum. Okay. And so he used discrete velocities, meaning like a list, not continuous velocities. So that's the opposite of continuous, where they can have any energy. Okay. So he introduced this as a mathematical simplification. That's a great place to start, right? And this idea, this germ of useful thought of quantized energies and Boltzmann's distribution of velocities infected Max Planck. So Max Planck, when studying black body radiation, and we'll talk about what that means in a second, used Boltzmann's discrete math, and it solved the problem. And he didn't like it. He struggled with it for years and said this was a desperate mathematical, grasping at straws to solve this problem. But it worked so well. And it suggested that nature might be discrete or quantized. And that was absurd, because why can't an electron have any energy that it wants? So this thing was picked up by Heisenberg as well. Now Heisenberg was similar to the positivists. He didn't care about atoms or particular particles or electrons. He just looked at the math. And he said, we're using this math to describe nature. It doesn't matter if the math is real. We're just going to use it. If it describes experimentation well, then we're good. Okay? But we're not going to read anything significant into the math. But Louis de Broglie, he wrote in his his PhD thesis that he could explain why electrons might have single energies or quantized energies if they behave like waves. So we talked last time about a guitar string, and it has a certain length and a certain mass and a certain tension, and it has certain frequencies that it can vibrate at. Okay, if you change the tension, then it can vibrate higher. Okay, and so de Broglie was saying, if you use a wave model, then you get this discrete energy behavior. And that was picked up by Schrodinger, who then was able to calculate the energies of electrons using this wave theory. And then Dirac pulled it even further and made wave mechanics. So this idea of waves started with de Broglie, got picked up by Schrodinger, and then developed by Dirac. And so it's combining the quantum thought of Boltzmann and the mechanics of Dirac. And so that's why we call it quantum mechanics. Okay. Mechanics before quantum mechanics was Newtonian mechanics. So sometimes your first physics class is just called mechanics. And it's the math behind cannonballs and pendulums. Okay. But this now is the math behind waves. So it was wave mechanics with Schrodinger, it was quantized energy levels, and so now we just combine those last two terms, quantum mechanics, and that's what we're talking about. So this is the math behind the waves of electrons and nuclei, and this describes how light interacts with matter. So let's get into the experiments as to why this was necessary. So what was it about nature that wasn't explainable with Newtonian physics? One of the things was black body radiation. Now this is a strange thing. If you heat up an object, it emits light, and this is a spectrum. So here we have, in terms of wavelength, 400 is blue, 700 is red. So here, this is the UV, the ultraviolet. This is the infrared. And this is a really hot object, okay, because it's emitting a lot of UV light. It's definitely glowing bright white because it's got a lot of blue light. All of the colors of the rainbow are right here. So our eye would see this light coming off of this object right there. And it would be a bluish white, really, really bright. And no matter what the object is, it gives the same spectrum. Now that's strange. Whether it's iron or aluminum, it's got to be something probably metal, because you're not going to get wood or anything else that hot. No fabric, no plastics, okay? But these metals, whether it was iron or steel or platinum, it was just a function of the temperature as to what color it was. That's kind of strange, isn't it? Okay, and so this was an interesting, curious phenomena that they were trying to study, and using classical mechanics, they were able to match, this infrared region. But notice how this line here goes up to infinity. That's the Rayleigh-Jeans law. So they matched the data down at the long wavelengths, but when it got to short wavelengths, it went to infinity. When Planck used Boltzmann's equation, which this is Boltzmann's equation right here. So this Boltzmann's idea is right there in the denominator. When he included that in the denominator, then when it got to the UV, it turned back around and went back down to zero. So whenever you're, like Rayleigh-Jeans law, it says it goes to infinity and it really goes to zero, that's seen as a catastrophe. And so this was labeled the UV catastrophe because they had a really successful law. And I think let's back up a sec and talk about law versus theory. Okay, it sounds like law is more important or more firm than a theory, doesn't it? I mean, we just hear this, it's a law, you can't break a law. But no, not in science. In science, a law is just a match of nature. You don't have to know why. If you just fit an equation to some data points in nature, then that's a law, okay? A law of nature. You're fitting it to the exact way nature behaves, okay? But you have no idea why. And so Rayleigh-Jeans law, they weren't saying anything about why it's matching, but they matched the long wavelength emission as a function of temperature, and so they had the Rayleigh-Jeans law. But it predicted that at any temperature, any object would emit an infinite amount of light. Any object at any temperature would emit an infinite amount of light. Where's it going to get the energy for that? It's not, okay? So even though they had a law that fit the long wavelength emissions, it wasn't a useful theory. This broke down because you're not emitting an infinite amount of light. Okay, so this black body curve was modeled by Planck, and the only way he could get it to work is if he thought about nature being quantized. Now this is interesting. This means that that every object is emitting some amount of light. And so here's an example of a guy with his hand in a black trash bag. In visible light, you can't see through the bag, but in infrared, you can see his arm. And so it's kind of interesting. And that's how our night vision works. Everything that's above absolute zero is exchanging energy with the environment in terms of infrared light. And so we can see in the dark if we have detectors on our eyes that look in the infrared. And that's how night vision works. And it's black body radiation. And it's just a function of temperature. So it doesn't matter, whether it's a person or an animal or anything or a tree. All of those objects are emitting light at different amounts because they're at different temperatures. Now, if you could get everything at the same temperature, then it would all blend into the background. And we kind of see that in some movies when they have thermal sensors and they try to get the room and the person is sneaking in there to steal stuff at the same temperature. That's trying to fool this black body radiation detector. So this is Planck talking about his solution to the black body radiation. He said this quantized energy was an act of desperation. He struggled with this problem for 6 years. Now, you've had troubles with homework before, haven't you? But 6 years on one problem? That's crazy. Okay. He knew the problem was fundamental, and so he went with the quantized energies, and it solved the problem. And this was a nice, what we say, beachhead for quantum mechanics, because from that point in, it explained a lot of different problems. So we had a very active physics community at the time. Ernest Solvay, this guy here in red, sitting at the head of the table. So Ernest was a rich philanthropist. He had a huge estate, and he liked to be around smart people. So he had these physics conferences where he would invite all of these physicists to his house, and they would argue about the latest theories of the day. This was an exciting time in 1911. You started to see quantization come into play, quantum mechanics. You also saw the nucleus and radiation being discovered, X-rays, alpha particles. All of this was on the table. And so we have people that you've heard of. I talked about Planck. I've talked about de Broglie. Here's de Broglie here. Let's see, some others that you may have heard of. We talked about Rayleigh-Jeans law, and here's number 3. Here's Jeans. Okay, I don't think Rayleigh's here in this one. Ernest Rutherford, this guy here discovered the nucleus. Here's Albert Einstein. Okay, here's Marie Curie. Okay, discoverer of radium and several other radioactive elements. Okay. Now, in freshman chemistry, you remember doing the Nernst law for batteries and so on. Here's Nernst over here. Let's see, it's number 6. Yes, these are a lot of famous scientists. Okay, and so one of the earliest experiments that confirmed Planck's law. So let's look right here on Planck's distribution law. Notice how there's a little h in here. This was introduced by Planck, this little h. He called it the elementary quantum of action, and it became known as Planck's constant. Now, another experiment that couldn't really be explained by Newtonian physics was photoelectron emission. You shine light on metal, and if the wavelength is small enough, or the frequency is high enough, then electrons come off of the metal. This is how a lot of our electronics work today. The first invention to use this was a vacuum tube. And so all of our amplifiers and so on used this kind of phenomenon. And so this equation that the energy of a particular photon of light or a light particle is dependent upon its frequency times Planck's constant. So this is Planck's constant right here. He called it the elementary quantum of action. So he's saying this little quantum number will turn a frequency into an energy. And then this frequency, the Greek character nu, is equal to the speed of light over the wavelength. And so now when you're walking across campus and someone says, hey, what's new? Just reply back, C over lambda. And they'll say, you've had Williams, haven't you? Okay, so that's definitely something to remember, because you need to be able to go from wavelength to frequency, from wavelength to energy, from frequency to energy, back and forth. These equations right here should be just like walking home, okay? Something you don't need to look at Google Maps for. So when a metal absorbs a high energy photon, it emits electrons. And the thing that couldn't be explained by Newtonian physics was that there was a minimum. There was a wavelength at which it didn't happen. So you see this slope here. You see the kinetic energy, so delta E here is a slope with respect to the frequency, and the slope is h nu. So the frequency times Planck's constant gives you the energy of these electrons. And so this confirmed that Planck's constant wasn't just about black body radiation, it was actually fundamental to nature. And this experiment is actually what Einstein got his Nobel Prize for. So Einstein, we know that he sort of came up with the standard model of the universe and relativity, and E equals mc squared, this sort of equivalence of mass and energy. But this is the solution that is such a simple solution that he got the Nobel Prize for. So this led to the description of light as a stream of particles called photons. Now, in terms of light, Newton thought light was a stream of particles. And now Einstein showed that light was a stream of particles. So this idea that light is particulate in nature had a lot of support. Newton and Einstein. Hard to go against them, okay? So this meant that light was a particle, not a wave. This is the basis of our modern detectors, photomultiplier tubes. Light comes in and electrons jump off of this photocathode. This is how our detectors and our UV and visible spectrometers work. This is also, at a smaller scale, how the camera sensors work. So light comes in, there's a bias on this little semiconductor chip, and an electron hops out of a stationary band and gets into a conductive band and gives signal, and then we turn that into an image. So this is still used today in all of our cameras. The reverse is kind of used in all of our screens. And so if you were to reverse this, you could put a potential across a diode, and when the electron hops across that diode, it spits out light. And so this photoelectron effect run in reverse gives us displays and LEDs. So this is just talking about this threshold at which, if you have light that's not energetic enough, it hits the electron, but the electron can't escape because there's this minimum energy, this quantized energy level that the electron must achieve before it can leave. And so this started us thinking in terms of energy levels, and that there being a level that the electron has to get over before it can be ejected. So this is where this idea of energy levels came from, was this photoelectric effect. Now, if the electron if the energy of the light is high enough, so this is the light coming in. Whenever you see h nu, we're talking about light. If the energy of the light hitting that electron is high enough, then it overcomes this barrier. This is called the work function. And you can put parentheses barrier. If it overcomes that energetic barrier, then it can leave the material. And it may have excess energy. So if the light is more energy than the barrier, then the rest of that energy goes into the kinetic energy of the electron. So the shorter the wavelength of light, the faster that electron can go. And this now allows us to accelerate electrons and to have fast electrons coming out. We can make electron beams with this, known as cathode rays. And so this is also where we get X-ray photoelectron spectroscopy. So we can hit things with X-rays and look at the energies of the electrons that come out. We will talk about XPS in this course quite a bit. The reverse of that is how we generate the X-rays. So we hit materials with electrons, and then they can cause a change in the material, and then that material can emit X-rays. So these are, we've turned these into techniques for spectroscopy. Now, what about waves? 100 years earlier than Einstein, Thomas Young had used the wave theory of light to explain diffraction. But because this contradicted Newton and later contradicted Einstein, his work was rejected. He gave a paper on this, and he said, look, this is a slit experiment where you have interactions of light, and it creates these patterns of light in dark areas known as diffraction. Can be explained if we think about light as a wave. And they just laughed at him. They said that his talk was destitute of every species of merit. And that's the way they spoke back then. That's a pretty bad takedown. You give your idea, and they look back at you and say, that has no merit at all. That is a stupid idea. And yet he was right. So poor Thomas Young. Yeah. And so again, these ideas were developed more at Solvay conferences. This is in 1927. And now we're starting to see the quantum mechanics folks come in. We have Schrodinger here. So here's Erwin Schrodinger. Here's Wolfgang Pauli. Remember when doing electron configurations in freshman chem, the Pauli exclusion principle, where no two electrons can have the same set of quantum numbers. Here's Heisenberg. So let's see. Debye, I'm not sure if you know Debye. He, the dipole moment is named after him. Okay. Let's see here. Marie Curie showed up again this year, and Einstein in the front. He's starting to look a little older. And then down here, let's see, who else do we have? Looks like we have Schrodinger. Here's De Broglie. Let's see. And then 9 is Max Born, and then Niels Bohr. So Niels Bohr, he's an important one next. He's trying to think, how can these electrons absorb and emit light? Well, let's think of it as the solar system. So how many people have seen the solar system model of the atom? This one here. I'm skipping ahead just a second. How many people have seen this in their schools? This is the Bohr model of the atom. And he's saying if light comes in and hits an electron, let's say it hits Earth, and maybe it could jump out to Jupiter's orbit. And so that the electrons have certain orbits around the atom. And if light comes in, you could absorb that light and jump that electron further from the nucleus. Now, why is that high energy? Well, because the nucleus is positive, according to Rutherford. And according to J.J. Thomson and Millikan, the electrons are also discrete particles. And they're very close to the nucleus. So they have positive and negative. They're attracted to each other. And if you pull that negative charge apart, you're absorbing energy. You're pulling charges apart. So the electron being further from the nucleus has higher energy. And if it wants to get closer to the nucleus, it drops in energy. Now, what they could not explain is what keeps that electron from crashing into the nucleus. So let's look back here at this earlier experiment. This is the first sort of atomic spectrometer. They would put gases in these little discharge tubes and run electricity through them. And then they would put a slit and just let a little bit of that light through, run it through a prism, and disperse it on photographic film. So photographic film was their detector at the time. And notice how the slit, and this is a sort of a linear gas discharge tube. You have this slit that's also a line. And so this line of light goes on to the photographic film and exposes a line. Okay. And so down here, what we see is individual lines of exposure on that film, and that's called a line spectrum. And these are, so that's a line spectrum, and these are spectral lines. So notice how it's a spectrum, that's the noun. If I want to use it as an adjective, it's AL, spectral lines. Okay, and so there's nothing magical about this line. It was just the image of the slit and the source that put it on the photographic plate. But what I want you to realize, vocabulary-wise, is we still call these spectral lines, even though our spectrometers are different now. Now, instead of these single lines, we'll see peaks. So a peak will go up and down like that. It might have a different shape and so on. But a spectral line and a peak are the same thing. And so that's more what our data looks like now. Is it's a spectrum, and it's got a peak and a valley and so on, but we refer to those as spectral lines. Now this is bizarre because that gas inside that discharge tube is hot. Why does it not look like a black body? Why does it not look like a continuum spectrum? It has discrete values. It has spectral lines. There's places where it emits light and places where it doesn't. That means sometimes it has this energy and it never has that energy. So these spectral lines could not be explained by the black body radiator. They couldn't be explained by Newtonian physics. They were a mystery. And Bunsen invented this spectrometer, just by the way, but he got the Bunsen burner named after him. So instead of the discharge tube, that was advanced. He was just putting salt in a flame, and he invented the spectrometer to look at the light that comes out of like fireworks, burning salts. And anyway, the spectrometer is way cooler than this little flame that we have. But he didn't get to choose, I guess. And so these atomic emissions are quantized, and Newtonian physics can't explain this. This led to this idea of atomic or electron orbitals. But the problem with an electron spinning around the nucleus is that why is it not like tetherball? You know, if you spin a ball, everybody played tetherball? It's a ball with a string on a pole. You spin it, and it slowly finds its way back to the pole. It doesn't have discrete orbits. Wouldn't that be a weird tetherball game where, you know, it's spinning around at a constant velocity and you hit it and it jumps out like that and it stays there. And then when it drops down, it spits out light. Okay, you're like, whoa, what's going on? This is an atomic tetherball. And so electrons do that. They jump out and then they jump back in, and they emit light when they jump back in. And so that's... So this idea of this planar orbit is a problem, and also what keeps the electrons out of the nucleus. And so de Broglie is the one that introduced this idea of waves. And so he said that this electrons around the nucleus, instead of being like a planet orbiting the sun, maybe it's like an oscillating cloud. And you've heard of the electron cloud. So get that in your mind. The electron is not like a planet orbiting the sun. The electron is like a cloud that's oscillating. So what you picture in your head is really important. Okay? So picture in your head the nucleus in the middle and this electron that's moving so fast around it that it is basically behaving like a wave that oscillates. Okay? And if you think of it that way, this semester will go much better. Okay, so when we show a molecular orbital, think the p orbital, right? Don't think of an electron going in a figure 8. Think of that dumbbell oscillating left and right. So the colors on the p orbital are how the cloud is oscillating. You can't point to any one place on there and say, there's the electron, okay? The orbital is the electron. That's the cloud. And a p orbital is oscillating left and right, or up and down, or in and out. Okay, and that's showing you how that cloud is oscillating. So this was de Broglie's idea that you have discrete standing waves between two limits. Now a guitar or a violin has hard limits, right? It has the bridge and it has the neck. And so those are the hard limits. What are the hard limits on an electron around a nucleus? Well, it can't be at infinity because it wouldn't be on the atom. So the cloud has to taper off as it goes to infinity, or we have lost the electron. So infinity is kind of a hard limit. It just approaches slowly, but still, it can't be at infinite distance. Now, why can't it be in the nucleus? You do have a process called electron capture, where an electron gets sucked into the nucleus and turns a proton into a neutron, and the atom's identity moves on the periodic table. We'll talk more about that in the spring. Okay, so it can get sucked into the nucleus, but it doesn't like to, because think about the volume it can occupy as it gets close to the nucleus. It gets smaller and smaller and smaller. So volume goes to 0 at the nucleus. And so that's a pinch point too. So just like a violin has 2 pinch points, or a guitar has 2 pinch points, where the wave has to stop there, the nucleus and infinity are the pinch points for an electron. And that can set up these standing waves, which we call the orbitals for the electron. Now that's a simple concept. Does it work mathematically? The answer is yes. Schrodinger, this is his paper in 1926, he took this idea that volume of the nucleus is 0 and the electron can't be at infinity, and put his math together. He actually had to get help from Hermann Weyl to help with the differential equations. And once he got the math, it took him a couple of months, then he solved the problem. And this is the emission, these are the emission lines for hydrogen, and he was able to solve them. Across the top is the observed spectra, and here's his theory. And notice it's not exactly perfect, but it matches really well. And so he just using his math and this idea of electrons being a standing wave around the nucleus, he was able to solve the hydrogen atom line spectrum, something that Newtonian physics couldn't do, black body radiation couldn't do. This was huge. And this is what really cemented the idea that quantum mechanics was a part of nature. Paul Dirac went and extended this in wave mechanics, and he made this incredible quote in his paper: "The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. The difficulty is only that these laws are too hard to solve." Meaning the math is too difficult. Okay? But if you can describe the electron, you can describe all of chemistry. Every reaction is changing bonds. What is a bond? A bond is just electrons holding nuclei together. So if you know where the electrons are, you know chemistry. It's just the math is too hard. And so we have these computational chemistry programs where we've thrown software and hardware at the problem, and now we're pretty good. We can do all kinds of gas phase reactions. When we get to liquid and solid phase reactions, it gets much more difficult. Okay. But we're going to learn this semester about how to use the Gaussian program to take this idea and turn it into real results. He also says because of this, it becomes desirable to have approximate methods of applying quantum mechanics that lead to explanations of the main features of complex atomic systems without too much computation. So this is what caused me to write a book. So I'm working on a book. The chapters that you will get on Blackboard have not been sent to the publisher yet, okay? And so if you find typos or anything like that, it's great. If you help me with corrections and things like that through the semester and say, this doesn't make sense, or it could be written better, I think, or whatever, have some suggestions, you'll definitely get acknowledged in the forward. So you can then see, oh, there I am. I helped him that semester. So it's up to you. If you don't have time, you got a busy semester, no problems, no pressure. But yeah, if you're like, okay, I kind of like this. I want to scour through this, look for typos or the math doesn't, he's dropped a subscript here or something like that. Welcome the help. I think it'll be fun. Now, let's get our mind around the density of the nucleus and the diffuseness of the electron cloud. So if you go to Target next, you'll see this big red ball. And this is the kind of stuff I do. My kids just shake their heads. We're walking along to Target one day, and I was like, man, if that were a proton, all right, how big would an H atom be? You know, would it be the parking lot? You know, my kids were like, yeah, probably bigger than the parking lot, you know, but we're just our minds. We're thinking, okay, the parking lot of Target might be as big as a hydrogen atom if this was the size of the proton. Well, it's more like 71 miles across. That one puny electron, average distance from the nucleus, you know, is 35.5 miles away. Yeah. So that's a big atom. Think about a sodium atom. So that 3s electron on sodium, it would be down in Argentina on average. Yeah. So when we talk about valence electrons being important for chemistry, that's all that's seen. When you're coming up to a sodium atom in Huntsville, Texas, and you get to Argentina, you're interacting with the first electron that you see. You have no idea what the core electrons are doing or what the nucleus is doing. Okay. And all of this comes from this quantum idea of a standing wave, that this electron is like a cloud. And so we're going to spend the first few weeks, a couple of weeks, looking at the analytical calculus behind quantum mechanics. And then we'll get into group theory, where we can simplify the math. And then we'll look at numerical methods, where you can actually do simulations of spectra. And so that's, we're just building up. We do what typically is done in this course over the whole semester. We cram into the first half so that we can do applications and applying our skills to real data. Because a lot of our students go on to industry, not everybody's going to graduate school, and so I like to provide practical, hands-on skill to all of you, because you're gonna need it. Okay, so this is, in summary, these 3 experiments revealed a quantum world, and wave mechanics solved all of them. Now we still have interesting problems to solve, like gravity. We still don't exactly know how that works. Okay. We have laws of gravity, but we don't have theories. We'll have theories, but we haven't confirmed which ones are the best. All right, so y'all have a great day.